Today, we're diving into something really fascinating from the world of AI research. It's a story about how one of the smallest, most subtle changes you could make to a neural network's design unlocked a surprisingly massive improvement in its ability to reason. So let's find out how they did it. So here's the big mystery we're going to unpack. In AI, we often hear that progress means bigger models, more data, more compute, right? But what if a smarter, more elegant design is actually the real key? This research puts that very question to the test, and believe me, the answer is genuinely shocking. And check this out. That's the result. On the absolute hardest problems, the new model saw a staggering 523% performance boost over its nearly identical twin. How is that even possible? To really understand this, we need to set the stage for a proper scientific showdown. So what we're going to do is look at a head-to-head competition between two AI models. They're almost exactly the same, built with the same components, their complexity carefully matched to make sure it's a completely fair fight. But, as you'll see, one of them has a secret weapon. Okay, first things first. To really get why the results were so dramatic, we have to understand the arena, the place where this test went down. And we're talking about one of the toughest AI benchmarks ever created, the Abstraction and Reasoning Corpus, or ARC. So what makes ARC so special? Well, it's all about measuring real, genuine problem-solving ability. See, it's not a test of memorization. It requires a model to look at just a few examples, figure out the hidden abstract rule, and then apply that rule to a brand new problem it's never seen. You know, it's a lot closer to how we humans actually reason. And this right here, this shows you exactly why ARC is such a beast. The AI gets trained on relatively simple tasks, like the ones you see in the top row. But then it gets tested on these much harder, out-of-distribution examples down below. The underlying rule's the same, but the complexity just skyrockets. This is exactly where most AIs just fall flat.
All right, so we got the challenge. It's tough. Now let's meet the two AI models at the very heart of our story. Think of them as two competitors, practically identical twins stepping into the ring.
In one corner, we've got a model called DARC, and in the other, a model called DAMP. Now, both of these are built to handle grid-like puzzles, just like the ones in ARC. And what's really crucial here is that the researchers put them in the same weight class. They matched their complexity, their number of parameters, to make sure it was a scrupulously fair fight.
So first up is DARC. You can think of it as our baseline. It uses a pretty solid, straightforward design. A convolutional layer just chews on the input grid over and over again, refining the information. It's a respectable approach.
And here is our second contender, DAMP. Now, at first glance, it looks exactly like its twin, DARC. But it has this one tiny addition, this secret weapon that, honestly, changes everything. It adds a small block called a channel-wise MLP. So what is this secret weapon? A channel-wise multi-layer perceptron. And the analogy here really helps it click. A standard convolution, which is what DARC has, is kind of like just stirring ingredients in a pot. It mixes things, sure, but this MLP, it's like a master chef creating a perfect emulsion, like making mayonnaise. You're forcing ingredients that don't normally mix to combine in these rich, complex new ways. It unlocks totally different combinations. So, to recap, two nearly identical models. One just has this extra fancy mixing block. The researchers threw 185 different ARC puzzles at both of them. Let's see what happened. The results are, well, they're pretty stunning. On the easier tasks, DAMP is clearly better, no question. But just look at the hard, out-of-distribution ones. DARC's median accuracy just craters. It plummets to about 2.3%. It basically fails. But DAMP, with that one little extra block, hits almost 15%. That is a massive difference. This bar chart really just says it all, doesn't it? That jump from 2.3% to over 14.5%, that's the 523% improvement we saw at the start. It's just an incredible leap in performance on the problems that truly test abstract reasoning, and it all came from that one tiny architectural tweak. But what's really fascinating here is how they performed. See, with ARC, there's no partial credit. You either get the puzzle 100% right, or you get a 0. It's all or nothing. So what these graphs show is that DAMP wasn't just a little bit better, it was perfectly solving these super hard tasks that DARC couldn't even begin to crack. And you know, even the researchers themselves basically say, look, this is genuinely surprising. Why? Because the models are so similar. You think that MLP block would be almost redundant. But just dedicating a specific component to explicitly and richly mix that channel information, it just unlocked this completely unexpected huge performance boost. So what's the big picture here? What does this all mean for the future of AI? This isn't just a quirky result on some niche benchmark. This finding could be pointing us toward a powerful and much more efficient new direction for building capable AI systems.
This discovery really feeds into a much bigger idea in AI called neural program synthesis. The ultimate goal is to create AIs that don't just find patterns, but can actually generate step-by-step programs or recipes to solve problems. We're talking about AIs that can think more systematically.
Now, a really promising path to get there is something called a hypernetwork. It's a pretty cool idea. Here's how it works. Step 1. A large network looks at a problem's examples. Step 2. Instead of solving the problem itself, it generates the entire set of parameters, the brain, basically, for a smaller, specialized network. Then, step 3. That small network it just built goes off and solves that one specific task. And this is exactly where DAMP comes back into the picture. For that hypernetwork idea to work, you need a target that's small enough to be generated quickly, but also powerful enough to solve hard tasks. And the paper argues that DAMP, being so compact and so capable, is pretty much the perfect candidate for this role. But here's the twist, and honestly, this is my favorite part about real science. The researchers are totally upfront about it. They don't fully understand why this works so incredibly well. The paper is very clear that the exact reasons are still an open question. It's just a great reminder that science isn't about having all the answers, it's about the exciting process of discovery. So let's just quickly recap the key takeaways here. Number 1, a small, elegant design change can give you absolutely huge performance gains. 2, explicitly mixing data channels is a really powerful technique for AI reasoning. 3, this points to new, more efficient paths for AI that go beyond just making models bigger. And finally, DAMP itself is a really promising building block for future research into neural program synthesis. And that leaves us with one last big question to think about. For years, the story of AI progress has been all about bigger is better. More data, bigger models. But this research suggests a different path forward. Is the next great leap in artificial intelligence going to come not from brute force, but from a deeper understanding of architecture and a search for more elegant, efficient, and powerful designs? It's a question that's going to shape the entire future of the field.